On top of an isolated peak in the Andes Mountains of Chile, a giant machine stands ready, recording. Do you know why? To completely revolutionize the way we look at the night sky. To tell the truth, that machine is attempting to show us a sight that no one in our history has ever seen before. We are in a situation where we might have to forget all the images of the universe we have seen so far. Don't we currently only have still photos of certain galaxies and nebulae isolated here and there? All that was like peeping at the universe through a keyhole. That era is over. What we are going to see next is not a photo. Instead of seeing a picture of the ocean, we are going to see its entire living ecosystem. The currents within it, the hunting creatures, sudden lightning strikes arising from the depths. No. In 2025, humans pressed the record button for a 10-year-long movie of this universe. On April 25th, that day was a test. But I don't know if you think I'm joking. This isn't entertainment. Instead, it is a massive investigation. After the highly intriguing mission of the James Webb Space Telescope, this is the biggest machine-based investigation conducted by the scientific world. A detective story seeking the fingerprints of dark matter and dark energy that we cannot see. A survival guide that identifies dangers heading towards Earth years in advance. A device that functions like a hidden treasure map, guiding us to phenomena we haven't even named yet. The name of this machine is the Vera C. Rubin Observatory. We are going to understand what it is going to do, because its discoveries will fundamentally question many of our concepts in physics. It will reveal to us many dangers we have gone without noticing until now. In short, we are not just taking photos anymore. We are going to capture reality itself, every single moment of it. To capture this picture of the sky without blinking even for a moment, the first thing we need is an eye, right? But calling the heart of the Vera C. Rubin Observatory a camera that takes pictures of the sky is equivalent to calling a supernova a spark. Its real name, or the real name of that imaging device, is LSST cam, which stands for Large Synoptic Survey Telescope Camera, the largest digital eye turned towards the sky. It weighs over 3 tons. That is, it comes to the size of a small SUV car. At its heart, there is a frozen digital retina. It's not a single sensor. It is a giant mosaic of 189 state-of-the-art sensors joined together, as seen in the picture. All these sensors are kept cooled at minus 100 degrees Celsius inside a vacuum chamber. Do you know why? To completely avoid electronic noise caused even by a little heat. Isn't there faint traces of light that started their journey from galaxies billions of years ago? Its job is to capture even those single photons. A 3.2 gigapixel image, when comparing to the megapixels in our standard iPhones or the 48 megapixels in a regular camera, this is 3,200 megapixels. That is the meaning of 3.2 gigapixels I mentioned. If we want to see a single picture taken by this camera in its full clarity, we would need a panel of more than 1,500 high-definition TVs joined together. Installed in front of this giant sensor are very large optical lenses. The largest among them has a diameter of more than 5 feet, from one end of the image to the other. These lenses show every star as clearly as a needlepoint. In between them, there is a robotic filter system. This observatory sees the universe through 6 different colors. From ultraviolet to infrared, 6 filters. If we can see the birth of new stars in ultraviolet light, in infrared, we can see stars and distant galaxies hiding between dust clouds. Every night, it will stand ready to use 5 of these filters. So we discussed such a big camera, but for light to reach that camera, it needs a mirror too, right? Here is where the Rubin telescope becomes an engineering marvel. This is not an ordinary telescope. It has 3 mirrors, and they are designed in a very unique way. The most unique feature of this is that its first and third mirrors are made from a single piece of glass. That is, a giant glass was taken, and its upper part was shaped as the first mirror, the primary mirror, and with a hole in the middle, its inner part was shaped as the third mirror, the tertiary mirror. So light falls on the primary mirror, hits the secondary mirror, falls onto the tertiary mirror, and then goes to the sensor. Thus, the main mirror in this has a diameter of 8.4 meters. That is the size of a double-decker bus. The surface of it is polished so perfectly that if you hear about it, You will be shocked. Aberrations occur only below 20 nanometers. To give an example, if the size of this mirror were the size of India, the highest hill on it would be less than an inch tall. Because of this design, the telescope can reduce weight, be more compact, and most importantly, capture a very unique picture of the sky without any distortion. But having the best eye in the world is of no use, because that eye must be able to move with speed. The need for speed arises because the universe does not wait for us. A black hole tearing apart a star might take hours. The trajectory of a dangerous asteroid changes in a day. To capture these events, we need extraordinary speed. The main large telescope inside the Vera C. Rubin Observatory is individually called the Simony Survey Telescope. That is the name of the observatory, Vera C. There is a difference in the name of the instrument sitting inside it. So this Simony Survey Telescope is not lazy. It is like an athlete. This giant telescope, weighing approximately 350 tons, moves not by using gears. Instead, it is on top of a thin layer of oil. Therefore, it can slide without any friction at all. Its ability is that this giant thing, heavier than a Boeing 747 aircraft, will shift from one spot looking at the sky to another in just 5 seconds. And it will stand steady there looking at the sky without any shaking. Just think about it, merely 5 seconds. Because of this speed, a special kind of dance happens there every night. The telescope moves to a spot, as you see in this video, opens the shutter, stops there for 30 seconds to get exposure and captures the picture, then closes the shutter, transfers the image to the computer. Within that time itself, the telescope will move slightly to the next spot. Then, taking the next photo in the form you see here, it goes to the next photo again. Like that, in this specific pattern, it will take approximately 1,000 pictures every night at 40-second intervals. You will understand when you see the pattern in which those pictures are taken. It covers a particular area, then goes to the area right next to it, covering it, and fills the pattern as it goes. Within just 3 or 4 nights, it will capture the entire southern celestial sphere on camera, because that is the southern hemisphere in Chile. Then what will it do again? It will start taking photos from the beginning again. Thus, for 10 years, every night without rest, it will keep continuing this. This is not just collecting photos. In truth, it is creating a live database, because it is a process of creating a live update on how our sky changes every minute. When such a big camera and such a big telescope come together, something that has never happened in scientific history will occur. That is, a real-time alert system notifying us of changes in the universe as they happen. Let me tell you a bit more pinpointedly how this telescope works. Today, this telescope took a 3.2 gigapixel photo. It will compare the photo taken just now on the computer with the perfect photo taken from the same spot yesterday. If it were an unchanging universe, no difference could be seen in it. But our universe is not like that. A newly appeared light, a disappeared star, an object that changed position, or any fluctuation in light, the computer will detect all of that itself. Every change detected this way will be turned into an alert. This alert will contain all information: its exact location, the change in light, old images, the smallest part of the new image, everything. It is expected that there will be more than 10,000 alerts from each picture. If the 1,000 pictures are taken in a night, it sends out 10 million alerts daily like this. This is the reason I called it a cosmic fire hose. The most important thing is that these alerts will be available to the whole world within 60 seconds of closing the shutter. It is like giving a message to scientists all over the world. Like, look here, something is happening here right now, you need to pay attention.
So what are we going to inform this world about?
These alerts are the key to finding answers to 4 big questions. 4 big missions. One of them is the dark universe. We have heard that everything we can see is only 5% of the universe. The remaining 95% is dark matter and dark energy, right? Rubin will measure small changes occurring in the shape of millions of galaxies and create a map of dark matter. Along with that, by discovering millions of supernovae, it will precisely measure the speed of the universe's expansion again. This will rewrite our very concepts about dark energy. The second is that it will detect and list millions of asteroids and comets. Most importantly, this is a planetary defense system. It is built to detect asteroids larger than 140 meters capable of destroying cities. Since they can be detected from very far away, we will get warnings months or years in advance. Just understand that this will be realized in a test lasting merely 10 hours. In its trial test itself, it discovered around 2,100 asteroids. The fun part is that 7 of them were newly discovered ones close to Earth. So that was just a test, but the reality is that it is currently discovering them properly. Now, another benefit is recognizing the moving universe. Don't black holes tear stars apart? Neutron stars often collide, creating elements like gold and platinum. Also, we can study changes in light caused by hidden planets. Rubin is also a factory for finding all of this. Previously, all this was luck-based testing. While looking somewhere, by chance, it would catch our eye. For example, the James Webb Space Telescope is looking at a small patch of the sky. But every minute, looking at a spot the size of 55 full moons, taking full details, looking at the next spot, taking full details, repeating this cycle. So this is not a luck test. It is scanning the entire sky in that area at the same time. Therefore, whatever event happens, we get an alert right then. Then, it is going to understand the story of our own galaxy as well. We know our galaxy, the Milky Way, sits like this. But what we have discovered so far is roughly only the area seen in this circle. The rest is our mathematical calculation. So, it will create a map of billions of stars in the Milky Way. It will help us understand how our galaxy formed and how it grew by swallowing other small galaxies. We can call it a kind of galactic archaeology. To build a machine like the Beamer on top of a mountain and monitor the data flood, the world needs a good location. That is the Cerro Pachon mountain in the Atacama Desert of Chile, approximately 2,700 meters above sea level. The specialty there is a clear sky without rain clouds. The observatory is built in a way that can survive even earthquakes. So who is behind such a massive project? Who is spending money on this? This is not a single country's project. It is jointly spearheaded by America's National Science Foundation and the Department of Energy. The country of Chile, where it is established, is also a major partner. Then, in the beginning, it is said that help from wealthy individuals like Charles Simonyi and Bill Gates was also received. Now, many have a doubt, when we have the James Webb Space Telescope, what is the need for this? To tell the truth, both do two different jobs. The Rubin telescope is like a wide-angle camera. It scans the entire sky very quickly and discovers where interesting things are happening, like a detective. At the same time, James Webb is like a powerful zoom lens. Rubin zooms into the place that says look there and allows JWST to study the things there in great detail. Let me say one more thing. For James Webb to capture the amount of sky Rubin captures in a single frame, it would have to take thousands of photos continuously. That is the difference. One discovers, the other studies in detail. They are actually a team, not rivals. Every night, approximately 20 terabytes of data is coming from there. Hundreds of petabytes of data over 10 years. There is a small twist in how this data is obtained. 10 million alerts, meaning about 1 crore alerts, will be available to everyone instantly for free. Anyone can verify this through science community brokers worldwide. But full resolution images and detailed catalogues of millions of objects will be available for 2 years only to scientists from countries that helped build it. It is like a recognition for their years of effort. After 2 years, that data will also be available to the world. That is, breaking news of the universe will be available to everyone immediately. But to get the full encyclopedia, one has to wait a little. That big dream we have been talking about for so long, that wait has had a beginning. Not just a hope, it has already happened. On June 23rd, 2025, the Vera C. Rubin Observatory released its first images to the world. To tell the truth, that was a historic moment. They released extremely beautiful images of the Trifid and Lagoon Nebula and the Virgo cluster, a galaxy group in the constellation Virgo. Along with that, some parts of galaxies and stars. These images were not just a sight. It was just the beginning of the massive mission to come in the next 10 years. A sample firework display showing the world how capable this machine is. A green flag shown officially to that journey for cosmic secrets like dark matter and dark energy. Everyone can see these images on the websites of the National Science Foundation and Max Planck Institute. Likewise, we are not discussing a future event. The first frames of that cosmic movie have arrived before our eyes. The scientific world is on the tip of the thorn of anticipation for what is to come. So, the movie filming of our universe, the universe seen from Earth, has begun. When 3 or 4 days pass scanning the entire sky, and the start of that massive mission officially begins. Anyway, the countdown to understanding the world around us has started. The biggest excitement of this is studying dark matter, understanding the whereabouts of dangerous asteroids, and recognizing galaxies, supernovae, and black holes. But that is not the biggest event of this project. It might discover things we haven't designed or even thought of so far. When building a device that is so big, fast, and sees so deep, the thrill isn't in finding just what we expect. It is that we must be able to find answers to questions we haven't even dared to ask. Mirrors have been polished. The camera has reached the mountaintop. Lights are all off. The projector is hot, and we have pressed the on button. Ordinary people will soon start getting a time-lapse of the universe. When we get that, what will appear on the screen to shock us first is the only curiosity remaining.